Let's take a look at a big picture of what's going on. Depending on which planet you're on, gravity is different. Why? Because each planet has its unique mass and unique radius. The bigger the mass, the stronger the gravitational field, right? The bigger the radius, though, the smaller the gravitational field because you're further from the center. And in real life, what happens is if everything that has mass has a gravitational pull, your body would be pulled by every single little part of the Earth in all sorts of directions, right? But the net effect is everything adds up going down because most of the Earth is underneath your feet. Downwards, that's accelerating down. So on Mars, gravity is about like a third less. The moon is like 6 times less. And then Krypton, one theory is, on Krypton, because gravity is so much more, like 100 times more, that's why when Superman comes to Earth, he's like so strong, because gravity is so strong. The first thing is think about how do you keep a satellite in orbit? We have to draw a free body diagram. What's a free body diagram? It's a picture of what? All the forces acting on a satellite in orbit. So here's what's weird. When a satellite's in orbit, what actually is pulling on it? There's just the pull of what? Gravity. The force of gravity pulls it into this circle. Is there any air resistance in outer space? There isn't. Is there any thrust you have to then maintain to keep it going? The answer is no. So what's weird is technically once a satellite's in orbit, it just stays in orbit. Think of the Earth's gravitational field as like a rubber band. It's like centripetal force. It provides rather centripetal force to keep pulling in a circle. So what's weird is once you get that satellite orbiting, you don't have to worry about it. So back to our little simulator here, right? If I fire this at the right speed, technically once it's in the air, the only force acting on it is gravity, pulling it back towards the Earth. But the Earth falls away, bummer, from the satellite, right? The Earth falls away from the satellite as fast as it falls towards the Earth and eventually hit what's called the escape velocity, which is very interesting. We want to figure out the radius of the satellite. So how do I find the actual radius? The altitude is what? The total height from the center or just above the Earth? Yeah, above the Earth here, right? So this is 20 kilometers in here. What do I have to add to that? I have to add to that the what? The actual what? Radius of the Earth, which is 6.4 times 10 to the 6 approximately, right? So the radius of the orbit is actually, the total radius is the radius of the Earth, 6.4 times 10 to the 6 meters, 6.4 million plus 20,000. And I know that doesn't seem like a lot, but it makes a difference. So we'll just punch that in our calculators really quick to get the total distance there. 6.4 times 10 to the 6 plus 20,000. You could also do 20 times 10 to the third, same thing, right? And it's like 642 blah, 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 right? So really simple trick, if you hit mode, you guys ever do this? Put it in scientific notation. It'll do it for you. 6.42 times 10 to the 6. It's actually not that hard to do, but you guys look a little tired. I'm going to teach you every trick in the book. 6.42 times 10 to the 6 meters. So now what we could actually figure out is how strong is gravity at that orbit. Is that important? It is, because depending on how strong gravity is at a certain orbit, it affects how quickly you need to launch your satellite. Otherwise, you don't get it into space. And it's a multi-billion-dollar industry. Let's go ahead and find G for that altitude. So again, if you look at our little table here, G is going to be equal to big G, the universal gravitational constant, times the mass of that planet over the radius squared. So we're going to take 6.67 times 10 to the negative 11th, our universal gravitational constant, times the mass of the Earth, which is 6 times 10 to the 24th kilograms. So notice it's such a big number, it doesn't really mean anything. And then we divide it by the radius of the orbit. So what should we use for our radius? 6.42. Yeah, it's not a big difference, but it's a little bit more. It's 20,000 meters above the Earth squared. So again, on our calculators, you just got to be very careful of order of operations. We do 6.67, the universal gravitational constant, to the negative 11th power. So normally gravity is a very weak force, but it affects us in a large way because there's a lot of mass around us. There's just a lot of Earth, a lot of stuff. Times the mass of the Earth, 6 times 10 to the 24th, and then we have to divide it by, this is tricky, the radius squared. Put it in parentheses, 6.42 times 10 to the 6th squared. So this, definitely you want to know how to use your calculator. We get gravity of 9.71. Let's round that off to 9.71. meters per second squared. And normally, on the surface of the Earth, it's 9.81 to be more exact. So notice, it's not a lot less, but it's a little bit less. And as we go further out, it makes a difference. So next, let's find the force of gravity at that point. So how do you find the force of gravity? What's that called? Force of gravity is also called weight, which is equal to what? mg, right? Which is the same as this whole big thingy, g m1, m2 over the radius squared. But we already did this part when we found that g of 9.71, right? So the force of gravity between the Earth and the satellite. So we have to take the mass of the satellite